Good morning. Today in this class we will discuss about potential formulation followed by gauge transformation. So our first topic is potential formulation in electrodynamics, where we will derive the equation connecting electric field and scalar and vector potentials. So we had already studied the Maxwell's relations, isn't it? Maxwell's equations in electrodynamics. That is del dot E is equal to rho by epsilon 0, which is the Gauss law. Del dot B is equal to 0. Del cross E is equal to minus dou B by dou T, that is the Faraday's law. And del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T, which is Ampere's law. So these are the four basic Maxwell's equations in electrodynamics. And it is clear that all these equations are of first order differential equations which connects electric field E and magnetic field B. In this small session, we are going to derive the relation between potentials and fields. We had already studied electrostatics in the previous sem, where we had an equation that del cross E is equal to 0. That is curl of field, electric field is equal to 0, so that we can represent E as minus del V. Also we have the relation Maxwell's equations del dot B is equal to 0. So since del dot B is equal to 0, B can be represented as del cross A. That means if divergence of a vector is equal to 0, that vector can be represented as a curl of a function. So from this Maxwell's equation, that is the second equation, del dot B is equal to 0. We can write B as del cross A, where A is the magnetic vector potential. So here A is related to B, or we can find out B using A. So in terms of magnetic vector potential A, we can write B as del cross A itself. So that is one main result from the second Maxwell's equation. But we know that here del cross E is equal to minus dou B by dou T, not 0 as in the case of electrostatics. So del cross E is equal to minus dou B by dou T. So this equation consists of both E and B. So in the case of electric field, it's not possible to describe electric field in terms of only scalar potential. Here we had already said that electric field can be represented as negative gradient of scalar potential, isn't it? But there the equation was del cross E is equal to 0. But here we have del cross E is equal to minus dou B by dou T. So we have to find an equation for electric field in case of the electrodynamics. So what we are doing is that we are taking this equation and we are substituting B as del cross A, so that we will get the equation connecting electric field E and potentials. I repeat, using the second Maxwell's equation del dot B is equal to 0, we can write B as del cross A. So that gives you the relation between magnetic vector potential and magnetic field. But here we cannot use del cross E is equal to 0. By equation, Maxwell's equation, we have del cross E is equal to minus dou B by dou T. So we have to find the equation for electric field that connects both scalar and vector potential. In electrostatics, we know that E is equal to minus del V. But it is not sufficient, since here in electrodynamics, del cross E is equal to minus dou B by dou T. So we have the equation del cross E is equal to minus dou B by dou T. So del cross E is equal to minus dou by dou T of, we are substituting B as del cross A. So rearranging, taking the right hand term to the left hand side, we have del cross E plus del cross dou A by dou T is equal to 0, or del cross E plus dou A by dou T is equal to 0. See, here we are having an equation that the curl of gradient of a function is equal to 0. That is, del cross del V is equal to 0. That is, curl of gradient of a scalar function is equal to 0. So you can compare both of these equations. Then you will get E plus dou A by dou T as minus del V. So that E is minus del V minus dou A by dou T. So this equation shows that this electric field can be obtained by combining both the scalar potential V as well as the vector potential A. So this is an main important equation connecting the field and the potentials. We have B is equal to del cross A. Similarly, E is equal to minus del V minus dou A by dou T. So now we had expressed electric field and magnetic field in terms of potential, isn't it? Now let's check for the Maxwell's equations whether they are consistent with these potentials. So prove that the following Maxwell's equations are consistent with the scalar and vector potentials. We have given two Maxwell's equations, that is del dot B is equal to 0 and del cross E is equal to minus dou B by dou T. Now what we are doing is that we are substituting the expression for B and E in terms of potentials here and check for this Maxwell's equations. So we have the first equation, del dot B is equal to 0, where you can substitute B as del cross A. So del dot B is equal to del dot del cross A. Now what will be that value? Divergence of curl of a vector is always 0. So you got a del dot B as a 0 itself, even though you had substituted B as del cross A. So the B is equal to del cross A is a valid expression in Maxwell's equation. Similarly, you can check for the second equation, that is del cross E is equal to minus dou B by dou T. So you can substitute E as minus del V minus dou A by dou T. So rearranging, minus del cross del V minus dou by dou T of del cross A. Now the first term again, the curl of gradient of a function is equal to 0 minus dou by dou T of del cross A. Dou by dou T of del cross A. Again del cross A is B, so del cross, you got a del cross E as minus dou B by dou T. So what does it mean? We had substituted B as del cross A in the first equation and we found out that dot B is 0. Now in the second equation we had substituted E as minus del V minus dou A by dou T. Still we got a del cross E as minus dou B by dou T. That means Maxwell's equations are consistent with scalar and vector potentials. Now we are writing the Gauss law and Ampere's law in terms of this electrodynamic potentials V and A. I repeat, we had the expression of Gauss law. Also we had the expression of Ampere's law. Now we are rewriting this equation in terms of scalar as well as vector potentials V and A. So that is the topic here. Gauss law and Ampere's law, considering the consistency of Maxwell's equations with scalar and vector potentials. So first we are dealing with Gauss law. That is the first Maxwell's relation, del dot E is equal to rho by epsilon 0. Now you can substitute E as minus del V minus dou A by dou T is equal to rho by epsilon 0. Opening the brackets, you will get del square V plus dou by dou T of del dot A, taking the negative sign to the right hand side. So it will be minus rho by epsilon 0. Now what we are doing is that we are adding and subtracting a term to the left hand side. And that term is mu 0 epsilon 0 dou square V by dou T square. So this term is added as well as subtracted, so that there will not be any change in the expression, isn't it? So this term is added as well as subtracted in the left hand side. So already we have this equation, that is del square V plus dou by dou T of del dot A. Now we had added this term and subtracted this term, and the right hand side is minus rho by epsilon 0 itself. Now we are rearranging this left hand side. We are taking the first term del square V as such. Now taking the last term as minus mu 0 epsilon 0 dou square V by dou T square. Plus, now we are having the second term and third term. Taking dou by dou T from second and third term, dou by dou T of del dot A plus mu 0 epsilon 0 dou V by dou T is equal to minus rho by epsilon 0. So that is the expression of Gauss law in terms of electrodynamic potentials. See, here you can see V term and also A term is there. So that scalar potential is there, magnetic vector potential is also there. So this is the expression of Gauss law, or we can say this is a Maxwell's equation which is expressed in terms of electrodynamic potentials V and A. So that's the Gauss law, started from del dot T is equal to rho by epsilon 0, and we have got this expression, that is expression for expression of Gauss law in terms of electrodynamic potentials V and A. Now we are moving to Ampere's law. What is Ampere's law? Del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. Again you can substitute B as del cross A and E as minus del V minus dou A by dou T. Now you can open the brackets. See, here there is a identity, that is del cross A. A cross B cross C is equal to A dot C into B minus A dot B into C. I repeat, A cross B cross C is equal to A dot C into B minus A dot B into C. So you can expand this term as del into del dot A minus del square A is equal to mu 0 J plus mu 0 epsilon 0 del into dou V by dou T minus mu 0 epsilon 0 dou square A by dou T square. Now let the mu 0 J term be on the right hand side and take all other terms to the left hand side, and you can rearrange it so that you will get the second term del square A minus mu 0 epsilon 0 dou square A by dou T square, that is the last term, minus taking the del from the first and fourth term, del of del dot A plus mu 0 epsilon 0 dou V by dou T is equal to minus mu 0 J. See, here there is only mu 0 J, but taking it to the other side, there will be a negative sign. So that will be minus mu 0 J. This expression also represents the Maxwell's equation, that is del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T itself, but in terms of V, that is a scalar potential, and A, that is a vector potential. So these two equations are important for us for the coming sessions. So in this session we had expressed this Maxwell's equations, that is del dot E equal to rho by epsilon 0 as well as del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T in terms of electrodynamic potentials V and A. Moving on to our next topic, Lorenz condition. So Maxwell's equation in terms of electrodynamic potentials V and A is given by, this is the equation which we had derived now. First one was Ampere's law in terms of V and A, and second one is Gauss law in terms of V and A. See, in both the equation there is a bracket, that is del dot A plus mu 0 epsilon 0 dou V by dou T, isn't it? So let this term be equal to 0. That is del dot A plus mu 0 epsilon 0 dou V by dou T is equal to 0. What will happen? This term and this term gets cancelled. So the first equation will be del square A minus mu 0 epsilon 0 dou square A by dou T square is equal to minus mu 0 J, and del square V, that is the second equation, del square V minus mu 0 epsilon 0 dou square V by dou T square, which is equal to minus rho by epsilon 0. So taking A from these two terms, you can write it as del square minus mu 0 epsilon 0 dou square by dou T square of A is equal to minus mu 0 J. Similarly, del square minus mu 0 epsilon 0 dou square by dou T square of V is equal to minus rho by epsilon 0. See, what is the advantage of giving that condition? That is del dot A plus mu 0 epsilon 0 dou V by dou T is equal to 0. Why we had given this substitution? See, here in the Ampere's law, you can see both, we had expressed this Maxwell's equation in both A and V, isn't it? The first equation contained both A as well as V. Also the second equation, that is Gauss law, consists of both A as well as V. So in order to reduce this expression containing only one potential, we are giving this condition. See, when we apply this condition, what happens to the first equation? First equation now contains only A. Similarly, the second equation contains only V. So these equations depends only on the vector potential A as well as scalar potential. So that's why we are imposing this condition, and this condition is known as Lorenz condition. That is del dot A plus mu 0 epsilon 0 dou V by dou T is equal to 0. And this term consists of both A and V, isn't it? Or we can write del dot A is equal to minus mu 0 epsilon 0 dou V by dou T. So this equation gives the interrelationship between A and V. That means a relation between the potentials, magnetic vector potential as well as electric scalar potential. So imposing that condition, Lorenz condition, we had written the equation as such, isn't it? So this term, this bracket is known as del square, and this operator is known as D'Alembert operator. See, this operator can be written in the form of a rectangular box. It's an operator. See, del square and dou square by dou t square is acting on A or acting on V. So this is an operator. So that operator is known as D'Alembert operator. So substituting with this symbol, we can write del square A is equal to minus mu 0 j and del square V is equal to minus rho by epsilon 0. So, in this Lorenz condition, we had substituted the Lorenz condition in the Maxwell's equations of Ampere's law and Gauss law, and we simplified it as del square A is equal to minus mu 0 j and del square V is equal to minus rho by epsilon 0. So what is the advantage of this Lorenz condition? Lorenz condition will help you to reduce the Maxwell's equation in terms of only one potential. Also, this Lorenz condition gives the interrelationship between A as well as V. Now, moving on to gauge transformation. What is meant by gauge transformation? We are making changes in potential without affecting electric field and magnetic field. So such transformations are known as gauge transformation. We know that potentials are related to fields. So we are changing the potentials so that there will not be any change in fields, and such transformations are known as gauge transformations. We know that magnetic field B is equal to del cross A, where A is the magnetic vector potential. Then we can represent A as a gradient of a scalar function, or we can add gradient of a scalar function to A so that it will not change B. See, we are having the expression B is equal to del cross A. Now we are changing A such that B will remain unchanged, so that we are having a new vector potential, and this new vector potential is represented by A dash, which is equal to A plus gradient of a scalar function, that is A plus del lambda. So even though we are making this change, there will not be any change in B. So such transformation is known as gauge transformation. Similarly, we can have a change in scalar potential also. See, we have the expression E is equal to minus del V minus dou A by dou T. We are subtracting dou lambda by dou T from V so that E is invariant. So that V will become V dash now. So that V dash is equal to V minus dou lambda by dou T. Here also V got changed to V dash, but substituting V dash here, there will not be any change in E. So that A dash and V dash are transformed magnetic and electric potentials respectively. And lambda, what is lambda? Lambda is a scalar and it depends upon the space as well as time coordinate. So what is meant by gauge transformation? We are changing the potentials A and V so that it will not affect the corresponding fields. Such transformations are known as gauge transformations. Let's go to the proof of this. Prove that E and B are invariant under gauge transformations. So first we are checking for the magnetic field B, which is equal to del cross A. Now we are going to find out B dash, which will be obtained by taking the curl of A dash, where A dash is equal to A plus del lambda, that is adding a gradient of a scalar function to that of a magnetic vector potential will give you the new magnetic vector potential A dash. So B dash is equal to del cross A dash. Del cross A dash is A plus del lambda. Opening the bracket, you will get del cross A plus del cross del lambda. Now what is this term? This term is curl of a gradient of a function, that is equal to curl of gradient of a scalar function is equal to 0. So what you will get? It is del cross A, that is B itself. So B dash is equal to B. So even though you have changed A as A plus delta lambda, A plus del lambda, you got B dash as B itself. That means B is invariant under gauge transformation. Similarly, you can check for electric field also. We have E is equal to minus del V minus dou A by dou T, isn't it? Now the new field will be E dash given by minus del V dash minus dou A dash by dou T. Now what is V dash? V dash is equal to V minus dou lambda by dou T, and A dash is equal to A plus del lambda. Now you can open the brackets. So it will be minus del V plus dou by dou T of del lambda minus dou A by dou T minus dou by dou T of del lambda. So the second term and the fourth term gets cancelled and you will get minus del V minus dou A by dou T itself. That is E. So that even though you have changed V and A here, you got E dash as E itself. That means E is invariant under gauge transformation. Clear? Okay, now we can move on to Lorenz gauge transformation. Already we had learned what is Lorenz condition, isn't it? That is del dot A plus mu 0 epsilon 0 dou V by dou T is equal to 0. So that is the Lorenz condition. Now you can apply gauge transformation to this equation. That means A must be replaced with A dash and V must be replaced with V dash. So what will be that equation? Del dot A dash plus mu 0 epsilon 0 dou V dash by dou T is equal to 0. Now A dash is A plus del lambda and V dash is equal to V minus dou lambda by dou T. Now you can open the brackets, so it will be del dot A plus del square lambda plus mu 0 epsilon 0 dou V by dou T minus mu 0 epsilon 0 dou square lambda by dou T square. Now already we know that del dot A plus mu 0 epsilon 0 dou V by dou T is equal to 0, isn't it? That is the Lorenz condition. So here you can apply the Lorenz condition. So the first term and the second term will be equal to 0. So what remains? Del square lambda minus mu 0 epsilon 0 dou square lambda by dou T square is equal to 0. Now what is that operator? That is del square minus mu 0 epsilon 0 dou square by dou T square. That is the de-Alembertian operator, represented by del square lambda, which is equal to 0. So this equation represents the Lorenz gauge transformation. So we had applied the gauge transformation to the Lorenz condition and we have got the Lorenz gauge transformation equation. I repeat, we had the Lorenz condition and we applied the gauge transformation to the equation and we got del square lambda is equal to 0, which is the Lorenz gauge transformation. Now we can move on to Coulomb gauge transformation. We had already derived the Gauss equation in terms of scalar and vector potential, isn't it? So that is the equation del square V minus mu 0 epsilon 0 dou square V by dou t square plus dou by dou t into del dot A plus mu 0 epsilon 0 dou V by dou t equal to minus rho by epsilon 0. Now, assume that there is a field that satisfies the condition del dot A is equal to 0. So what happens to this equation if del dot A is equal to 0? Del dot A is equal to 0 means that this term will get cancelled and this term will be mu 0 epsilon 0 dou square V by dou t square. And there is another term minus mu 0 epsilon 0 dou square V by dou t square. So this term and this term, that means second term and fourth term gets cancelled. So what will remain? Only del square V. So del square V is equal to minus rho by epsilon 0. And that equation is Poisson's equation. And we had how we got this Poisson's equation from the first equation? We applied a condition that is del dot A is equal to 0. And this condition is known as Coulomb gauge. The condition del dot A is equal to 0 is called Coulomb gauge, and on applying Coulomb gauge, the Gauss equation reduces to Poisson's equation. Now what is this advantage of this Coulomb gauge? Why we had applied del dot A equal to 0 into this equation? Again, this equation consists of both A and V, isn't it? So it is difficult to solve this equation. So in order to solve this equation, we have to make this equation having only one term. For that, we had substituted del dot A is equal to 0, and that condition is called Coulomb gauge. And we have got this equation as del square V is equal to minus rho by epsilon 0. So what happens? On integrating this equation, you will get V, that is the electric potential, isn't it? So that is the advantage of Coulomb's gauge. On applying Coulomb's gauge, this equation reduces to this equation, and on integrating this equation, you will be able to determine the scalar potential V. But we know that even though we had got scalar potential, we cannot determine E, because E can be determined only by finding out A also. So E is equal to minus del V minus dou A by dou T. So that is the advantage of Coulomb gauge, to find out the electric potential easily. So that's about the Coulomb's gauge transformation. So we had already learned what are the potentials related to the fields, that is the magnetic vector potential and scalar electric potential. Now we had expressed the Maxwell's equation in terms of electrodynamic potentials V and A. And in that equation, we had imposed a condition which is Lorenz condition, and we found out the Lorenz gauge transformation. And also we imposed a condition known as Coulomb gauge, that is del dot A is equal to 0. And we can find out the value of V easily by substituting the Coulomb's gauge in the above equation. So that's about the potential formulations and gauge transformations. Here also we had already written the Ampere's law, isn't it? Here we had used the Gauss law. Now you can write Ampere's law. See, del dot A is equal to 0. Apply the Coulomb's gauge equation in Ampere's law. You can derive this equation. So Coulomb gauge is often used when there is no source of charge. So no source means potential is equal to 0. So that E will be equal to minus dou A by dou T. I think the class is clear to you. Thank you.